So we're going to be looking at graph theory, and it's not like the graphs you think of when you think of algebraic graphs. It's quite different. And in fact, you're going to find it probably a lot easier than the algebraic graphs you might have seen in the past in high school. So let's take a look at the idea of this. Suppose that a town has 7 bridges, as pictured here. We want to create a graph that could be used to determine if there's a path that crosses all the bridges at once. So say you are making some sort of delivery and you gotta go to all these different regions, so you're gonna have to cross all of these bridges. Or maybe you're a construction worker and you've got to go to these bridges for some reason. But we're gonna cross all of these bridges one time. We're gonna try to do it in the most efficient manner. Now, all we're going to concentrate on at first is drawing a graph of this situation. Later on, we'll concentrate on finding the shortest path. And you can see why someone would want the shortest path. For example, a mailman wants to go the least amount of distance, doesn't want to walk through everything twice. Or a truck driver needs to go the least amount of distance in order to have the lowest cost as far as gasoline. And of course, the lowest wear and tear on the vehicle. So there are many reasons why we want to find a path that is short. All right, so first though, we've got to get some terminology and we've got to get used to this idea of graphing. So here, since we have these bridges, we're going to let them be what we call edges. And we're going to let the land masses be what we call vertices. All right, so to understand this better, I'm going to call this the North Shore up here. I'm going to plot a single point and I'll call it N for north. And let me get a smaller print or finer pen there. All right, and I'm going to call, and then there's this landmass right here on the left. I'm going to put another vertice for it. And since it's to the west, I'll call it W. And then there's this island in the middle, so I want another vertice that represents the island. I'll call it I for island. And then over here, there's this landmass that we will call east. We'll call it the east landmass. So I'm going to put another vertices for east. So notice our vertices are really just points representing the land in this case. All right, and then we have this southern shore down here, and I'll call that south. Okay, now I'm going to draw lines in between these according to where the bridges are. So let's notice first of all, from the north to the west here, there is a single bridge. So we'll have a single bridge. All right, from the north to the island, there's also a single bridge. And then from the north to this east landmass, there's a single bridge. Now let's also note, let's start right here. From this west landmass, there's an island down to the south, or there's a bridge down to the south. From the island here, there are actually 2 bridges to the south. So we'll do it like this. There's 2 bridges. And then from this east landmass, there's a bridge to the south. And we don't have any bridges going in between here. So that is our graph of this situation. Okay, so notice that I called each of these points vertices. Each of the lines, these are edges. So our vertices are these points, and then the lines in between are edges. So let's just get a few more definitions now that we know kind of what a graph looks like. Let's see if I can get this to go onward. So the degree of a vertex is the number of edges coming out of it. For example, S up here, let's notice that S has 1, 2, 3, 4 edges coming out of it. So it has degree 4. A path is any series of edges from one vertex to another. All right. So, for example, we could have a path from S up right here to N. We could have a path that goes from S to I and then from I to N. Okay. There's also something called a loop, and we don't have a loop in this particular graph, but a loop is an edge that starts and ends at the same vertex. So, for example, if I had a loop coming out of S, it would start and end back at S. Okay, so that's what a loop looks like. Now, of course, we didn't really have a loop there, so I'll just erase it. All right, and then a circuit is a path that starts and ends at the same vertex. Now, let's realize with a path, it's going to go to other edges. So it's going to go to other vertices. So we might, for example, in this situation, we might have a circuit that goes from S to E to N to W and back to S again. So we can think of a circuit if you think of electricity, a circuit has to be connected. It goes out and then it comes back to that same node or vertice again. All right. And then weights. Later on, we're going to see some graphs with weights. Weights are values put on each edge that represent things like distance, cost, or anything else that we might need to minimize. So, we might need to minimize the distance that a trucker is going across from one point to another. And of course, we want to find that shortest distance. And that's what we're aiming at, is finding shorter distances. All right, now we're going to look at something called Dijkstra's algorithm. And there is a set of sequences in the book, in your textbook, and it's very complicated. In fact, I think I've got it here somewhere. Dijkstra's algorithm in the book might be here. Has a series of long, complicated instructions. So here's the instructions in your textbook, and I just think it's very difficult to understand what the instructions are saying. So we're going to do an example, which I think will make it a lot more understandable. So I'm going to bring this example into play, and we're going to do Dijkstra's algorithm on it to find the shortest path. Okay, so let's say a truck driver has to get from, or maybe you need to get from Tacoma, Washington to Yakima, Washington. And Tacoma is a T and Yakima is a Y. Don't know if I'm pronouncing that right. But we have to, there are different routes. We can drive through Auburn, we can drive through Mount Rainier, we can go through North Bend, Eatonville, and Packwood, but we want to find the one that is the shortest as far as time, and the weights that are on here are weights of time. All right, so let's look at how to do this. So first, we begin by putting right next to our destination, that our distance, or our time in this case, to our destination is 0 if we're in that destination. All right, now we're going to work our way backward, and we go backward along each path. All right, and what we're going to end up doing is putting the shortest distance as we go backwards. So let's notice that if we look at the shortest one, that's P, 76 minutes. And if we go backwards, that is going to be 76 minutes to Y from there. Now, we also want to mark, though, the next one is going back to Mount Rainier, 96. So on that vertex, we're going to mark 96 minutes. And then same thing for North Bend, it's 104. Now, it becomes a little more complicated now as we go backward from these vertices. So there is only one way backward to E. So in that case, we're going to add the 76 that we've already talked about, minutes here, to the 96. And that E will be that many minutes away from Yakima. So let's see, 76 and 96 going backwards is going to be 172. So far, not all that complicated, but now let's go backwards from Mount Rainier. All right, now Mount Rainier, we can get to Mount Rainier in a number of ways here. We can come from P, which is Packwood. We can come from A, which is Auburn. But let's note several things. Our final destination is Y. So if we think about Mount Rainier and North Bend working backwards here, really we want the shortest route here between these two. And the shortest route is the 36. So if we go back to A, we are going to add 36 to 104, choosing always the shortest route, or in this case, the least amount of minutes. Okay, so we're working our way back to previous vertices using the least amount of minutes. All right, now, if we work our way back to T, there are two pathways backward to T. There's a 20 and a 57. The shorter one, and we have to think of adding these to what they're coming from. 140 would make this 160. If we add 57, though, certainly that's going to be bigger than 160. So the shorter route is going to end up being this one that adds up to 160. So really, if we think about what led to that 160, here's the path that we would want to take to get the shortest route, 104 minutes plus 36 minutes plus 20 minutes. And Dijkstra's algorithm leads us always to the optimal, or the shortest distance, or the shortest amount of time in this case, that we might need to follow.